Hi there, good afternoon. Yesterday there was a thunderstorm and the computer just went boop. I thought I'd just continue with this one here. Okay. Yesterday we stopped on the use of this standard reduction potential. And it's very important to see that it's called standard, which means this thing like that now. E standard, right? At the temperature 25 degrees centigrade, 1 atmospheric pressure, and it's reduction, not oxidation. Because why reduction? All the E0 values given in the data book is reduction. Remember this. So don't go and change it. See, all is reduction. Whatever here is plus electron. So this value here is positive. Now this is the standard standard reduction, right? It's a standard reduction potential. Okay, so quote this value here or this value here in your answers, but you can voice it in a different way, that's all. So to fit into the marking scheme. All right. So now these are called reduction potentials. Okay, right, which means all this will follow your standard electrode potential. You don't call it standard reduction potential, you call it standard electrode potential in your data booklet. Okay. Now, of course, we took the first one here. This M and M2 plus, M, which means they talk about, like, for example, titanium. Okay, titanium. Okay, Ti. Yeah, like here. Sorry, here got already. Ti2 plus goes to Ti. That means this is reduction, isn't it? Okay. Now, of course, for the other end is copper. It means Cu2 plus aqueous plus 2 electrons, reversible, Cu solid, and the E0 value here is plus 0.34. Now, to use this value here to talk about applications, right? Because in normal day, like you and me, right, we talk about applications in using the metal. This one here, not the ions. If it goes this way, if it oxidizes, that means it's going to be rusted. See? So the point is, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper, do they really last? Or they get corroded easily? Iron rust easily, but that's it, really? Okay. Titanium, we use it as for those expensive cameras, Nikon, light and very hard. We use it, of course, I told you before, and it's a heat bone joint or all the sockets there. In the body is filled with water and oxygen. Will it rust? It seems not to. Chromium is used for stainless steel. It doesn't rust, right? See, all your plates and all the surgical stuff, well, they are, spotless clean, no rust. Otherwise, you die. Okay, so the two things in nature that will cause it to oxidize, that's to rust. It's of course acids on metals, right? Because metals become M2 plus, right? And of course, the other one is water and oxygen. I call it the Batman and Robin. I think I'll stop here right now. I stop this point here, right? Where this part here, metal, okay? For acids, of course, you can see all this, right? Because it's going this way, it'll be positive, 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 positive. Only this is negative, which means that from nickel to titanium, it will all be destroyed by acid. They will all, react with acid to give you your salt. Copper won't, except copper nitric acid. I don't know where I told you this, but you can see here, right? Nitric acid, copper. In nitric acid, the H plus is not the the oxidizing agent. It is this one here, nitrate. The nitrate has 3 here, 1, 2, 3. You have to use the first one, which gives nitrogen dioxide, the brown gas. Okay. So this nitrate is very powerful. Nitrate is a very powerful oxidizing agent. It's used to preserve meat, nitrates and nitrites, and it seems that it's used in sausages. And you eat too much of sausages, it can cause cancer. It seems they found evidence in America that those kids that eat more than 10 or don't know, something like that, sausages, they are very likely to get leukemia. So beware, okay, because this is used to preserve meat. Nitrates, okay, you can check your luncheon meat, they got nitrates and nitrites, right? Okay, luncheon meat especially, sodium nitrate and sodium nitrite. I checked it before. Okay, now this one here is able to go to NO2 plus water, okay, it's positive here. So if I put this nitric acid, H plus already here, right? in copper, it will oxidize copper, because copper is going backwards here is minus 0.34, and nitrate is plus 0.81. So you round it up, you can see that, well, it gives you a E cell of positive 0.47 rewards, which means what? Feasible, what? Feasible. That's why it can be corroded. That's why, you know, all those statues, all those brass and whatever statues, right? It's the nitric acid that actually will destroy it, because the green color stuff that comes out is actually copper nitrate, right? Now, so I can see from here, right? Everything is destroyed by acid. Now, how about oxygen and water? Well, it is supposed to be very durable. See the things now. Titanium, the most famous titanium, light and strong. Now, titanium here. Titanium is a metal we use in your hip joint or whatever, or your bone replacement or whatever, or your cameras, which is supposed to be very lasting and not be able to oxidize, but it will oxidize it. If it goes to here, this is plus 1.63. The reduction potential is minus 1.63. Yeah, you can see here, reduction, that is oxidation, reduction. Yep, 1.63. So I'm using it backwards, okay? So now for the Batman and Robin, water and oxygen, a famous duel. These two here, right, to form OH minus is plus 0.40. You can see here, you don't believe me, right? You see here, right? Oxygen. You have to know this, and this is a very famous electric potential here, okay? Oxygen plus water, and they can take 4 electrons. This is the same thing that causes iron to rust, okay? 4 OH minus, and it's positive 0.40. So if you put that inside here, like here, put down here, okay, right? This is titanium plus, okay, and this is your water and oxygen. See, so overall you form titanium hydroxide, and it's positive. See, the E cell is positive. E cell here is positive 2.03, very large, you know. That means it will occur. So titanium will rust, titanium will destroy. Not really, because the oxide and the hydroxide will form a layer on top of the titanium metal and will prevent further rusting. Same thing when in the steel companies that they make all those big steel, no, they will actually rust it first. They will dip it in nitric acid and rust the top part, no, and the top part is covered with a layer of iron oxide. That's why those bridges can last so long. Okay? Same thing. Isn't that aluminum? Aluminum is very active, isn't it? And once you take aluminum, the oxide will form a layer and will be permanently protecting the bottom part of the aluminum. Same thing here. Okay. So remember, titanium until your nickel, cobalt, all this will form a layer. They all will react with your water and oxygen, okay, to form this layer here, and will further reduce and in fact prevent further oxidation of the metal. That's why these TM metals are so useful. Okay, chromium, stainless steel, right? Chromium oxide will form a layer, and that's it. No more chromium will no longer be oxidized. Okay, chromium metal. So this is the application for this one here. Now, how about this electric potential? Okay, 3 plus to 2 plus. Remember, again, going this side here is receiving electrons and plus electrons. That means reduction. Okay, now we go across it now. What does this tell you? Well, it tells you 2 things. First, of course, remember across for all the TM, plus 2 and plus 3 are common. Plus 3, right? They're common. But is there something more stable or not in the beginning and at the end? They found that in the beginning, plus 3 here are more stable than plus 2. And in the end, plus 2 is more stable. Here is a half-half, no? Here +2 is more stable. But can you prove it not? You can. You prove it from the standard reduction potential. Now remember this 3 plus going to 2 plus, right? Which means like here, titanium 3 plus equals plus electron go to titanium 2 plus now. And it's negative. 3 plus to 2 plus. Negative means what? It means not feasible. Not feasible. Which means +3 is more stable. That's why +3 is more stable at the beginning. Titanium, vanadium, chromium. Come to manganese, +2 is more stable. See, manganese here. Manganese, right? +3 go to +2 is, see, so +2 is more stable. Not because it's 335, but because it's just more stable. Why? Because, see, as you go across the period of your TM, to take out the third electron from the +2 is harder, right? Not because the nuclear charge is increasing. Like for example, I'll tell you, okay, here, okay, right, for titanium, right? Titanium, I think is 22. Let's check. I don't make a mistake. 22 titanium. Yeah, 22 protons. Yeah, 22 protons. Not first, 22 protons. Okay, and of course, manganese is 25. So let's go back to there. Okay, so titanium got 22 protons. Okay, manganese got 25 protons. Okay, now if it's 2 plus here, right, 2 plus here, and I want to this 2 plus here because the 4s is empty, so the 3D here. Okay, the 3D here. So to remove the 3D, there are 3 of them. Okay, to remove it, to remove it here, okay, right, is easier than to remove it from here. Because why? The distance is shorter and it's 25 to 22. So the attraction of the nucleus towards this outgoing electron, right, the third electron, is harder, isn't it? That's why it's harder. So +2 is more stable. Okay, because to remove the third electron from +2 is harder. Okay, so now mind about that. Okay, so now you can see across here. So application for this one here, the trend of stability of +2 across the period. It means go across here, +2 is more stable. In the beginning here, +3 is more stable. Here's +2 is more stable. Okay, you can see from the standard electric potential value. Okay, where it's negative, it's going to positive. But the second thing is, of course, if it's more stable, it means that the 3 plus here, the 3 plus here, see for 3 plus, for M3 plus, A equals, to go to M2 plus equals, it must accept electron. That means that this is an electron acceptor, which means it's an oxidizing agent, right? Okay, so as you go across the period, the oxidizing agent of +3 will increase, right? Yeah, because you go across the period here, right? It becomes more positive. That means that they are able to accept electrons easier. See, so M3, that means titanium 3 plus and cobalt 3 plus. Who is a stronger oxidizing agent? Cobalt 3 plus, because it's what? It's positive. See, you compare two. Let's say for example, titanium 3 plus here equals plus electron. To go to titanium 2 plus equals, right? Now the E naught value is how much? It's minus 0.37. They will ask you to quote one. Okay, cobalt 3 plus equals plus electron. Go to cobalt 2 plus equals, how much is positive 1.82, sorry. Right? So these two fellows here, let me put it red, okay? These two fellows here, this fellow here and this fellow here, they are both electron receivers. That means they are both what agents? Oxidizing agents, right? To become the 2 plus. But who is a stronger oxidizing agent? Of course, you can see it from the E naught value is a plus 1.82. It means it's stronger. It's more feasible, is it? So across the period, the oxidizing agent for +3 becomes stronger. See, increasing. in oxidizing power of +3. Okay, so two things you can see there. Across the period, +2 becomes more stable. Across the period, oxidizing power of 3 becomes more powerful. Okay, now the other thing, of course, is we're going to talk about these two further here. Okay, Mn3 plus and Fe3 plus. Because these two also, if it's 3 plus here, they act as oxidizing agent. The question is this here, right? The question is this. Mn3 plus is a stronger oxidizing agent. That means electron acceptor. And iron 3 plus, Fe3 plus is a weaker oxidizing agent, electron acceptor. Explain. Okay, basically, right? Remember? Okay, let's go back to here. Now, Mn3 plus, right, is Ar3D4. Okay? Mn2 plus Ar3D5, right? That means if it accepts electron, it will go to Mn2 plus, which is Ar3D5. This one have got what? Extra. It's not very, very stable, but it's extra stability because of the half-filled 3D. So the extra stability make it easier to go forward. Okay? Right? The extra stability that means that it's really to go forward more. That means to give you the shifting of the thing towards to right hand side makes it more positive value. That's why you see plus 1. See up here. Normally this is a normal trend. Okay, normal trend for the rise in the E value. Okay, so it's gone up here from maybe 1.7 whatever, 0.75 is going to 1.49 whatever here. The extra stability, that means extra positiveness to go forward is because of the 3D5. Now iron is supposed to be here, right? The iron, because iron is going to from a 3D5, is iron, where's iron? Okay, iron here. Iron here, okay? Now iron 3D, this is the +3. Iron 3 plus Ar3D5. When you receive electrons, it means it acts as a what? Oxidizing agent. It receives electron. It means it's going to a Fe2 plus, which is 3D6. 3D5, 3D6, who is more stable? 3D5 is not. That means it's unwilling to go forward, but it will go forward now because it's positive. Right? It's still positive. It will go forward, but it goes forward unwillingly. Okay? That means it go forward, that means it must be oxygen. That means it acts as oxygen, but not as strong as it's supposed to be. Okay? Weaker than normal. That's why, because of the 3D5. Okay, it's very simple to explain. Okay, so now I finished all these things about here. So now let's go to the other one, which is your complex ion, which is the huge chunk here, right? Complex ion formation. Now in complex, what does it mean by complex ion? There are a few things you must understand. In complex ion, right, there is a central atom or ion. Very important, central. That means there's only one. Normally there's only one in the formula, with only one species, I would say. Okay? Or it can be ion, it means a charged particle, or it's a positive charged particle, it can be negative, or an atom which is charged 0. And of course, there must be things surrounding it which are called ligands. Okay? There are ligands, they can be atoms or molecules that contains a lone electron pair. Okay, that surrounds this. Surrounds this and will form dative bonds. Okay. Now I'm going to show you a couple first before then I go to the definition. Okay. Now this is like this. So, okay. Now we have not seen this before, probably but you actually have come across this kind of substance before. This is just iron 3, like when you dissolve iron 3 chloride in water. Right? Okay, it goes in water on a form IFE3 plus aqueous plus 3Cl minus aqueous. This is this. Aqueous means that the water will surround it. This water is called a ligand or ligand. Okay. The lone pair of oxygen now, water here is neutral, isn't it? Neutral, there's 6 of them. Okay. So there's 6 of them here, and each of them, the lone pair here forms a dative bond. Okay, this one is called ligand and it's called monodentate. This one lone pair can form one dative bond. This is called the central ion. Now this is 3 plus here. This is called ion, but there also can be atoms. No, like for example, Fe pentanyl carbonate or carbonyl 5 is a like that. Fe, okay, CO, OC here. This is your okay from dative bond here. Okay, OC. Now this is of course carbon monoxide. All right, this is charge 0 atom. Similar with nickel in the Mons process. That's how you purify nickel using the same thing, carbon monoxide, and this is square planar. Okay, nickel here. Okay, OC, 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 OC. Okay, so you can see all these are your complex ion. They contain a central ion, in this case element 3 plus, and F minus here, right? These are the ligands. Same thing with this one here. This is the famous copper 2 tetraamine. You remember now, okay? In your form 5, you call it copper 2 tetra. Tetra means 4. Tetra amine. Amine means here's your NH3. Okay, NH3. Okay. Now here they put water inside. Very important because it will form an octahedral complex. See, octahedral mean, remember not? That means okay. Right, octahedral complex. Okay. So these are called complex ion. Now let's look at the definition given in your syllabus that actually will fit into exactly what the marking scheme says. Right, now here. Describe, remember here, general characteristics of chemical properties of the first set of transitionals, titanium to copper, blah, blah, blah. Describe and explain the reactions of transition elements with ligands, okay, ligands, to form R complexes, including complex of copper 2 plus. Now remember, the stress copper 2 plus and cobalt 2 plus and copper 2 plus. And with what ligands? Water, which is H2O. Why H2O? Because you got 2 lone pair here. Now they can form dative bond. Okay. And ammonia, same thing. All right. Lone pair here, dative bond. Okay. And hydroxide. Remember hydroxide here is negative charge now because there are 3 lone pairs. It's negative here. And of course, chloride now. These are all like molecules of 2 things in chloride can. They got 8 negative. Okay? Can form. Right? So we're going to look at all this. Now they ask you for define. They define the term ligand or ligand as a species. They contain lone pair of electrons. Very important. It's so important that I want to tell you that you better pay attention. There are 3 things here. They'll ask you for the ligand. They ask you what's the ligand. I show afterwards, okay? Now here it contains the lone pair. And ligand must contain a lone pair, the lone pair. Okay? At least 1 lone pair of electrons. They can form what? 2. Dative bond. Dative bond. Okay, dative bond means what? The covalent bond is formed from 1 source. The source provides 2 electrons. Normally, a normal covalent bond, each of these partners will produce 1 electron. Okay? But here, 1 partner, 1 fella provides 2 electrons. And to where? Central, number 3 point. Central atom or ion. So is it right now? So now these 3 points here give you the marking scheme I told here of your ligand. Hold on first, including monodentate. That means dental means 1 teeth. Means 1 teeth to bite the fella. The biting is the covalent bond. Very strong, it won't break one. Bidentate means 1 fella, one ligand got 2 sets of teeth. It means it form 2 dative bonds. Polydentate means one fella can form many bonds. This is EDTA. Now let's look at this definition first, okay? Ligand, right? And I'll show you the question on ligand and of course page 84 and the definition, okay? I show you it comes out. I'm not bluffing you. See? what is meant by the term ligand, or ligand in the context of transition metals. Okay. Now, I've got two definitions here. You can see it well. See, a ligand is a species that contains first mark. No mark. Two things, one mark. Okay, there are three things here. Give only one mark. Contains a lone pair of electrons. Okay, at least one lone pair. Okay, a lone pair of electrons. And what is lone pair electrons do? That will form a dative bond. The lone pair electrons will form a dative bond. 1 point here, 2 point. 2A, I said third point here, they no, they don't care lah, as long as you got these two things here, give one mark already. A lone pair of electrons that form a dative bond, mark, but that's still right. Two mark here. 2A metal, a central metal here, central. Remember? Central metal atom or ion. Okay, see now. This is enough or lone pair donor metal, blah blah blah. So the 3 points here, a ligand. A ligand is a species that contains a lone pair, at least one lone pair. They form a dative bond to a central atom. Okay, now you can see another definition here. I think is here. No, here. Okay. Right, see here. Ligand. An ion. Okay. Now they say ion, of course, it can be an atom, isn't it? Right. An ion. Right, an ion. That means it's okay. When the ligand. Oh, sorry, this is not the one. This is actually complex ion. Wait, sorry about this. I think it's over here. Ligand. Okay, a ligand is a species. Remember, right? A ligand is a species. It's a species that contains a pair of electrons that can form a dative bond. Say 2 points are there. Two, of course, they bracket here. That means you don't have to put it, or you put it better, of course, you show you know something to a transition element. Right? To a central atom, which is a transition element. Okay. Now they ask you here. I show the question. All right. They ask you the ligands. Okay. Okay, now here. Decide which of the following species could be a ligand and which could not be a ligand. Put a tick. Okay? Remember OH here. OH, OH. Oxygen got 1, 2, 3, 4, 5, 6. Okay? The 7 because it's negative, right? It means got extra electrons here. I used to ask my students, where did the extra electron come from? From where? OH. No. Oxygen got 6 here. 1, 2, 3, 4, 5, 6. But one more here. Where it come from? You don't care. Come from sodium. So what anyway, come from potassium, whatever, you don't care. As long as there's the negative sign here, that means that there's an extra electron here. This is from your hydrogen here. So there are 3 pairs here. Right? That means they can form it. Either one of these 3 pairs will form the dative bond with the central atom or ion. Okay? NH4 cannot already. Nitrogen 5, is it? 1, 2, 3, 4, 5. No. This one bond to here, bond to here. This ammonia. Ammonia cannot. But if you come with the H plus here, you go to the H plus here to form NH4 plus here. It means no more. Cannot. See? This one can, because oxygen got 2 lone pairs. This one can. This amine got 2 lone pairs here. So all can. Except this one cannot. Right? Now they come in this form, or give another one. Ligand. There's another one. Ligand. Okay, anyway, I show you the marking scheme. I'm sure that I've got it here. I don't know where the window is. Okay, it's on here. Never mind. Okay, they actually asked you for. Never mind. I thought I got it here. No, ligand table coordination number. Definitions, I think, okay, let's try 1, 2, 4. That's last time. Okay, now mind. Okay, let's go back. All right, you know what I'm saying, isn't it? Right, a ligand definition. Okay. Okay. Now, how about complex ion? Now, complex ion, this definition I gave 2 things, guys, I forgot. It's going to wait. I hope I can finish this on time. Okay, now it says here, complex ion, ligand. This one is define the term complex or complex ion as a molecule. It means no charge, charge is 0, or an ion got charge. The charge can be positive or negative, cationic, or anionic. Okay, that means the complex, I mean positive, negative, or 0, charge 0, right? It's formed by a central atom. Can be an atom, that means no charge, or ion, surrounded by one or more ligands. Okay, now this is the definition. Now let's see. I give you here from, I copy from this book. I don't know what book is it. Okay, thank this guy. A complex ion is formed when a number of ions or molecules. Now this a number of ions or molecules. This is the ligands. Okay, these are the ligands. Okay, ions means they are charged. For example, OH minus, Cl minus. Okay, the charged particles. Okay, or molecules. Or molecules, of course, can mean NH3, no charge, or H2O, no charge. Okay, these are common ones. Combined with a central, the central atom. Central here, of course, is the transition metal. Can be atom, I told you, like for example, nickel in a Mons process, right? 4 is no charge, this is 0. Or your iron, no charge, carbonyl, 5, 0. Atom of iron to form an entity. The entity here is a complex ion. Complex ion, in which the number of ions or molecules, which is the ligands, directly attached to the central atom by what bonds? Attached by dative bonds. Exceeds, and this is very important, exceeds the normal covalency or oxygen of the atom. Atom here, of course, ion of the TM or whatever. For example, see, you've done this in, of course, your AS tolerance region. Remember, tolerance region is silver nitrate plus ammonia, isn't it? You get silver diamine like that. Now, this is your complex ion. This is your tolerance region. You do it like this one. And the whole thing here is 3. The whole thing here is positive. Why? Because it's positive. Ammonia is no charge. So how many ligands, how many bonds are formed? Okay, see? The number, see the number of ions, number of molecules directly attached. How many here? 2. 2 of them attached to here exceeds the normal covalency. It means 2 is greater than 1. Why? This is the normal covalency. 1. See? Same here. All this is iron 3 plus. How many dative bonds attached to here? These are called the coordination number. Coordination number is the number of dative bonds attached to it. Dative bonds are not necessarily ligands, okay? Dative bonds. How many? There are 6. So exceeds the normal 3. So it's called complex ion. Aluminium is 3 plus. There are 6 F minus here. So it exceeds. Same thing, all these things here. Cobalt 2 plus is 6 NH3. Copper 2 plus is 6 molecules here. Okay? So exceeds the normal covalency, right? That one they didn't bother. Okay, now let's look at how they the question on complex ion. Okay, page 75. They actually asked. See, 75. 75. 75. Here, where is it? Here. Explain what is meant by the term complex ions. 1 mark. Okay. Now here's the definition, which I taught just now. See, it's a very simple one. An ion, a complex ion, is a complex ion. It's formed when a ligand, okay, or when ligands datively bonded to a central metal or cation. Okay, all they want is ligands, central atom or cation, and dative bond. 3 important things. Okay, they don't care how many are there. Okay, and another definition here. I think 2. Okay, here. A complex ion or complex is a compound, can be a compound, which means there's no charge. Species, molecule, all these are just general terms of ion formed by a central metal atom of ion. there must be a central ion, which is the TM. Surrounded by or bonded to one or more, right? One or more. The formula number is more, like, can be one, actually. Okay, unless it's a neutral further. Okay, bonded by some ligands or groups, right? Through what? By dative bonds vector. Okay, so there must be ligands or groups or molecules of iron. Now, of course, the ligands here cannot be positive charge. They're either ions or they're neutral. The central atom cannot be negative charge. Can be positive or neutral. Okay, so a complex ion is a molecule formed when the ligands, right, which contain lone electron pair, form dative bond with a central atom or ion. Full marks. Okay. Now they also ask about coordination number, which means the number of bonds formed. Now before that, just let me go back to here a couple of definitions first. Okay. This thing called here 21. This thing called donor atom. Okay. Now remember definition here finished. Okay. Now as I said, complexes can be neutral. Like I give you here example. No charge. No charge. Cationic, got charge. Got charge. Here I want to show you because normally copper tetraamine is written with the water. This is my old notes, which is wrong. Okay, put H2O here, put 2 here. Together they make an octahedral complex. 2 plus. Okay, this is very important. You can see here they actually I see or not. Okay, I want to show you that actually they put it down here. Okay, marking scheme. You cannot run away from marking scheme one. Okay, of course they say is they don't minus marks, but no, but better give the correct one, is it not? Okay, I don't know where is it. Okay, this should be around here. All right, now see not here. See, now this is, they give both answers are correct. See, the copper tetraamine or, see now, the one with water. I prefer water, why? Because they can draw the octahedral complex like that here. Okay, draw a square here, copper 2 plus here, and here is your ammonia. Okay, now you must learn to draw 3-dimensional. You can see, sometimes all of them are in 3 dimension. Okay, right? This is your NH3. You must draw. Don't just draw lines, and draw all these 3-dimensional. Okay, it's NH3, and up here is your water. Down here is your water. Okay, sorry, too fast. I'm trying to catch up with time. We got 15 more minutes. Okay, right? So let's go into here. Okay, anionic, this is a very common one, copper tetra. This is copper, this one here is a tetrahedral, like that. Famous one. Okay, coming out here, going back here, and these two are straight. Okay, Cl. This is all Cl minus. The whole thing here is 2 plus, this is 2 minus. Okay, this is yellow color. You must know the color also. Okay. So now here are the few terms. Ligands or donor atoms are called normal ligands. Okay, they are neutral, no charge. For example, ammonia, water. Okay, or anions, which are OH minus, Cl minus, and F minus, and so forth. Are able to form dative bonds. But you must understand here. They always say ligands what contain species contain a lone pair, at least one lone pair. A lone pair must have a lone electron pair that can form dative bond. 1 mark for this, 1 mark for this, and 1 mark for to a central atom. Okay, they bond to a central atom. Remember, always remember, always keep in mind. Okay, ligand. Not this one here. Ligand contains a lone pair of electrons form a dative bond, right, to a central atom. Remember this. Okay, definitions Just follow what Cambridge said. Now, donor atoms, now they don't use so much. Donor atoms is the atom in a ligand that is bonded directly to the central atom. For example, in ammonia, right? In ammonia here. Well, yeah, okay. Now remember ammonia, right? Is NH. Now this whole thing is called a ligand. But nitrogen is the one that is responsible for giving up the lone electron pair. This is called a donor atom. Okay, donor atom. That actually forms the dative bond. Okay, the donor atom. All right, so now let's go on first. I'm going to bring monodentate and all these things, okay? Now, coordination number is the number of donor atoms, right? Number of donor atoms, not the number of ligands, no, it's the number of donor atoms, or you say it's a number of dative bonds, or the number of dative bonds. Form with the central, the central atom. Now, let me show you the markings in this, okay? Coordination number meaning, okay, is 137. I'm not bluffing you one. You always must see how the question come up and how to answer it. Okay, here. What is meant by coordination number? I don't bluff you one. 17 May, June 41. I hope I can find it somewhere here, the coordination number. 17 May, June 41. Okay, here. 17 May, June 41. Okay, here. All right. Coordination number. Where is it? I see. Hold on. Let's see. Ayo, mana dia? Okay, 17 May, June 41. What number is this? Number 3. 17 May, June 41. 17 May, June 41. This one? 17. No. Sometimes, ayo. Yeah. Okay. 17 May, June 41. Now here. The number of bonds, coordination number, you can take it down or whatever you want to do, or eat it, whatever, I don't care. You know, thumbs up. See? Coordination number is the number of bonds. It means number what? Dative bonds. Or the number of atoms. This will be the donor atoms. Okay? Not necessarily ligands, no, because a ligand can have 2 donor atoms. It's called bidentate, see? Okay? Number of dative bonds or atoms bonded to an atom, okay, to a central, this is put in black and all, right, bonded to the atom of iron metal or the central metal, the central, okay, bonded to an atom of iron species in the central metal, okay, can be number of dative bonds or number of donor atoms bonded to it. Because you can say, sometimes you can have a bidentate. I'm going to show you, okay, now here. All right, where, okay, let's go back here, 21. 21 Okay, notes here, you can say, you can see here, okay. Now, okay, classification of ligands according to number of lone pair of electrons. Monodentate, okay? Monodentate, right? They have at least, not just one pair. Some got only one pair, like ammonia, only one lone pair. No. Oxygen, you got 2 lone pairs, see? Right? Monodentate, 1 lone pair that has at least 1 lone pair. I forgot to put something here, but this marking, marking same. 1 lone pair that can form a dative bond with the central atom or ion. You cannot only say 1 lone pair. But 1 lone pair can form a dative bond. Always remember with the central 3 points here. It's just like ligand. But mono means 1. A bidentate, right? That means this is 1 ligand, but contains 2 donor atoms here and here. These are diamine, see? It's like this. N, H here, and CH2, very common. So one ligand, but two donor atoms, they can form two dative bonds. They're called bidentate. Hexa means a big fella here can form six. EDTA is special one. I'll show you what EDTA is. EDTA is very useful in industry because it will cause things to be stable. It will coagulate things. It will take up heavy metals. You can read all here, okay? EDTA. Now this EDTA, this is one ligand. No? 1 year they give ask you to circle where are the donor atoms. EDTA got many. See, all got lots of lone electron pairs. But what is important here? Which are the lone pairs that will bond? See, they form a very nice shape. They can just nicely fit the structure inside here. Like the lone pair here. Lone pair. Because lone pair, there are three lone pairs here, but one lone pair will form. Okay, he got lone pair, but it doesn't form. See now. You got 1, 2, 3, 4, 5, 6. You got 6, 1, 2, 3, 4, 5. This minus here. 1, 2, 3, 4, 5, 6. So see now, this one form. So one ligand, right? And you got 6 donor atoms. Can form what? 6 dative bonds. What with the central atom or ion? This central atom or ion. So what's the coordination number? 6. Okay, coordination number 6. This is called hexadentate, or normally call it a polydentate. Okay, let's go back to here. So I'm going to show you what they want you to talk about here. Okay, see, polydentate. Okay, now, right? Polydentates are so-called, they are called chelating agents because they form a claw or bite. Now, the method of biting is very strong. They're all covalent bonds. Dative covalent bonds are very strong. Okay, so here, I'm going to show you examples of how they ask these things. Okay, coordination number, ligand, and all the rest of the tests. Okay, page 124. I think I cannot go further. Never mind. Okay, 124. See here. For each of the following complexes, state the coordination number, oxidation number for transition electrons. That's another discussion. Okay. Now, nickel, you must understand nickel always form a square plane. Now, I see sometimes, maybe I should have gone this. Never mind, let's go back here. Okay, I want to tell you the types, the type of shapes first before I jump the gun. Sorry about this. Too excited, very good. See, the types of shapes, okay? Stoichiometry, they call it shapes, stereochemistry and stoichiometry. Shapes. Okay, the shapes, there are basically 3 shapes or 4 linear. Octahedral. Why octahedral? Octa means that 8 sides. Like here, say if you put like this one, okay, copper lah, water lah, okay, water, okay, water, remember, right? If you don't know, I'm sure you know, this is lower 6. Each pyramid here got 4 sides, 2, 3, and 4. So total there are 8 sides or 8 planes. That's why it's called octahedral. Okay? So whenever there's 6 coordination number, right? Always octahedral. EDTA or 6. Right? Then there's square planar. Nickel always forms square planar. Nickel and platinum are famous square planars. Remember this. Okay? NP. No play. Okay? No boy, no people, no play. Right? Always got square planar, that's square planar. Nickel always square planar. Cn, which is minus, no. Okay? What Cn is like that one? Okay? 2 lone pair here, negative here. Because 4, 1, 2, 3, 4. This one come from somewhere. From where? Don't care. Because this one got 1, 2, 3, 4, 5. No? Okay? Yeah. So this fellow here will form the bond. Okay? Square planar. Platinum also square planar. Tetrahedral, copper, I told you, can form octahedral. Whenever don't form octahedral, they form tetrahedral. Very simple. C, 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 three of them. C, 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 and Cl. Always with chloride. Copper chloride, cobalt chloride, and chromium chloride, all tetrahedral, sp3. Right? Why? Why don't form square planar? Because the chlorine ion is very big, so they cannot squeeze into the angle of 90 here, like the 90 degrees here. They rather go on 109. Okay. Cl. No, this is 109, isn't it? 109.5. This is 90. So too hard to squeeze here. Okay. So they spread out. Okay. So, and then this octahedral. So very simple. When there's 4 coordination number, they either form a square planar, which is for nickel and platinum, or tetrahedral, which is called CCCC. Okay, this is remember. Right? If the coordinate number is 6, it's always from octahedral. It's linear, for example. This is not in our syllabus, but silver is what is still here because of your organic chemistry, which is a tolerance reagent. This is copper 1, no. Copper 1, no color 1, it's only 1. Copper 1 plus formed by Cl minus and Cl minus here. And this is linear. 90, 180 linear. Okay? Now let's look at some of these examples. 1, 2, I'm very conscious of the time, okay? We finish with this, okay? 1, 2, 4. 1, 2, 4. Yeah, 1, 2, 3, 1, 2, 4. Okay. For each of the following complexes, state the coordination number, oxidation number of the TM present. Okay, nickel, right? So nickel, you can see here, right? So of course, this is 2 plus 2, 4, isn't it? Coordination number 4. Of course, if you draw it out, you can draw sideways, looks more beautiful, okay? Nickel, all right? Cn here, and H. Now remember, I'm showing you this is the first part, okay? First part here. The angle here is all 90. So this 4. Of course, Cn can be over here, isn't it? Then you get the isomerism, cis trans isomerism. Later, okay, down later. Okay, relative epitite first. Coordination 4. What's the oxygen number? You must know that this minus, this 0, this 0, and the whole thing is no charge, no charge. That means nickel must be plus 2. Remember, plus first, plus 2 again. Number 2 plus wrong, no. 2 plus is salah, wrong, cannot. Coordination number is always plus 4. Now, chromium. Remember this 2, 2 and 4, 6. So what is your 6 here and it's tetrahedral, sorry, octahedral. Okay, very simple. Of course, there are 2 again, Cr here. You can put the Cl anywhere, up and down. It doesn't matter first, okay? Because I told you later you will have this called cis and trans. So because they didn't ask you what Cl here, put Cl here, okay? And then water here, okay? Water, OH2, here's water. There are many things I didn't teach you yet. This is just a third thing. Now, first this Cl is minus. The whole thing is charged positive. So this has to be 3 positive now. Yeah, so it's plus 3. See? State the type of bond that exists between the ligand and the metal. I also is it covalent law. State the structure of this name is shape. Easy, is it? What is this tetrahedral? This is your flat planar. No? Name the shape. Okay? Now this one later. Now let's look at the marking scheme. I think 16 November 42. Yeah. 42. Hold on first. Mr. I forgot to give this one. Number 42. Hold on. 16 November 42 marking scheme. 16 November 42. See, I prepare all the 16 November 42. 42. Okay. One more thing. 16 November. I say sorry. 42. Okay, 42 is here. All right. Okay, let's stop here. Okay, and screen share. Okay. Saw my face. Okay, 42. All right. Okay. See here? All right, see now. Coordination number. Yes, plus what? Plus 4. Yeah. Okay, plus 4 ma. And see, plus 2 then. Plus 2. Plus first and 2. Okay, this is 6. Chromium is plus 3. Dative bond or covalent bond. Okay, so the structure here. Okay, right. Now let's go to 2 more questions, then we're done now. Okay, right. Now another one, of course, is table 38, page 38. I won't show my face again. 38. Oh. 37. Oh, 138 lah. 138. Okay. No. 138 here. This is more challenging. Complete the table by predicting appropriate coordination numbers, formulate charges of the complexes CD. Okay. This common 3 plus a bit bigger. Okay. 3 plus coordination number. Right, CN here. Now it can be anything one. Okay. Because chromium normally is has got 6 one. So it's coordinate number 6. Okay. So it's this octahedral. Chromium normally forms octahedral. You have to know that. Octahedral. That means this one will be 6. It means it's CR, CR, CN, 6. Okay. The whole thing. Remember, this -1 is -3, charge 3. Okay? That's why we put here, -3. Correct one. Okay. 6 ma? This plus 3. Coordinate number is 6. Or they actually tell you lah. Okay, remember now this is by dating 2, 1, 2. Yeah, yeah. Nickel told you it's a flat, it's a square planar, isn't it? Okay, but they say coordinate number 6. Right? That means they want an octahedral. See not? Right? That means they have, means in this case here, nickel. So normally is square planar is a coordinate number is 4, but now it's 6. So 6 means it must be an octahedral, right? So we put a bracket here. And H2, CH2, CH2, and H2, bracket here, how much? 3, see? The whole thing here, bracket, what charge? Remember? Now, this is charge 0, isn't it? Nickel plus 2, so it's plus 2. 2 plus. Okay. 2 plus. See? The right minus. Now, here I wrong already, so be careful. When the charge here, you must put the number first. Because they put the numbers, the number first, right? So it's 3 minus, here's 2, okay? So it's 2 plus, okay? Now, platinum is always from a square one, so they leave it to you, okay? When number is 4. Platinum, I tell you, nickel, they have 4, right? And 2 also, they have 2, of course, right? Okay? So it's PT, remember the flat molecule here, PT, Cl, 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 Cl. It's 2 plus. It's minus, 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 minus. The whole thing is minus 2. 2 minus. So plus 2. Here's formula is PT, Cl, 4. Bracket. What? 2 minus. So all these hints they give you. Now this is a famous ethane dual ion. This one here. Okay, remember now. Okay. Minus here's this is also a bidentate now. Yeah, famous bidentate. 2 here. Okay, bidentate. So they say that that's 3. Right? That means they form each bidentate forms 2. Coordinate number is 6. That's not right. I'll show you the thing later. Okay. So remember each one, there are 3, each one give you 2. There are 2 minus here. 3 of them, 6 minus now. Here's what? 3 plus. So holding is 3 minus. Clear? Okay, now go and think about it. One last one, 137. Oops. Mr. Lai got it all wrong. Never mind. Okay, I thought 137 here, I don't have. Maybe it's one here, the coordination number. I thought there was one more here. Okay, never mind. All right, I think time's up. I would continue with the complexes later. Tomorrow, today is Chinese New Year, man. Hey, I'm still working, huh? You guys better work. Okay, so I'll see you tomorrow. I hope so. Goodbye. Stop sharing. Okay, stop recording.